Hello, everyone. Thank you for coming and for joining us for a session about Amazon Redshift. My name is Rahul-Pathak. I'm the Senior Product Manager for the service. And you'll also be hearing today from Anurag Gupta, who's in the front, who's the General Manager and my boss. So I'll make sure I say the right things here. But what you'll learn about today will be an overview of Redshift, how we set out to achieve performance, ease of use, and deliver it to you at a very low price. And then Anurag will come and talk to us about some of the things that we've been working on over the past year and some of the upcoming features that we hope will be useful to you as you think about Redshift in your own architectures. So Amazon Redshift, it's a fast, easy to use, petabyte scale data warehousing service that costs under $1,000 per terabyte per year. And when we were thinking about Redshift, our design points were we wanted to deliver a system that was 10 times faster than row-based stores for analytic queries at a tenth the cost of traditional systems. And I'll talk to you about how we set out to achieve that. So one of the things to keep in mind when you're doing data warehousing and large-scale analytic queries at scale is that I/O and being efficient about how you do it and doing it fast is critical to achieving performance. And so Redshift is a columnar data warehousing system. And what this means is, unlike a traditional row-based database, where if you wanted to sum, say, the amount column, you would have to read every single row in your table and then throw away 3 out of the 4 rows, which is inefficient because we don't care about 3/4 of that data for this query. In a columnar system, you can only focus on reading the data that you care about. And so you do 1/4 the amount of I/O, you get the result you need. And the reason this is beneficial is if you think about it, most analytic queries are not, get me everything I know about this person. Most analytic queries are, I want to know all the orders that happened, or I want to know all the totals. I want to know which items were purchased. So they operate on a subset of the rows in the table, and you're able to get much better performance for these kinds of queries. Another big benefit of columnar storage is compression. And so because you have like data stored sequentially, what you're able to do is then apply the compression algorithm that's most appropriate for each column. Each column is stored independently. And when you actually load Redshift using the copy command, which is a bulk SQL load command that automatically loads every node in your cluster in parallel, Redshift will sample your data and then automatically pick the compression algorithm that's best for the data that you have at hand. You can always analyze this. The output you see on the right there is the result of running an analyze SQL command on a table. You'll see that each column has a different compression algorithm or has one that's most appropriate for its data. And you can always override this when you're defining your tables, which you do using standard SQL statements and DML statements. And the benefits of compression for you are really twofold. And our customers typically see anywhere from 4 to 8x compression on real-world data sets. This is an average. What you might see that some columns compress much better than others. For example, if you had something which was storing just Boolean values, it would get much better compression. And with compression, what you get is more performance. And the reason is that every single read that you do contains more relevant data. So if you think about 4 to 8x compression, if we read a single block, we'll get that much more relevant data for the queries. The other benefit is cost. So if you have a 4 terabyte database that collapses down to a 1 terabyte data warehouse in Redshift, you've just saved yourself a ton of money on storage and on computing capacity. And again, this is done automatically for you. The third technique that Redshift uses to deliver performance is an idea called zone maps. And what zone maps do, and they apply best for sorted columns, you're able to keep track of the minimum and maximum values in every block. So if you think of a table that might contain event data, say hits to your website, and you're logging that, it unfolds in time, and you have your table sorted by time, if you write a query that has a range in it in your where clause, say show me all the data for the past month, Redshift can use these zone maps to skip over blocks that it knows won't contain the data that's relevant for the query because it knows the minimum and maximum values per block. And again, you'll see this theme of being efficient about doing I/O, avoiding it when we don't have to, and being intelligent about our knowledge of the data to give you better performance. At some point, though, we're going to have to go to disk. Sorry. We will have to go to disk to do our reads. And Redshift runs on a hardware platform that's really custom designed for high throughput data processing. And so it's based on the EC2 high storage instance. It comes in two sizes. The extra large has 16 gigabytes of RAM, 3 disks on it, with 2 terabytes of compressed storage. So if you're getting 4x compression, you can store 8T on that machine. And there's a creatively named 8 extra large, which is 8 times as big on every dimension. So 128 gigs of RAM, 24 spindles, 16 cores, and 16 terabytes of compressed storage. And with these, you get over 2 gigabytes per second scan rate. And the idea is that we want to give you local disk so that you can get maximum performance. But then as part of the management of the service, we take care of replication and backups and durability, so you get the benefits of local storage for performance, but managed storage for ease of use. From an architecture perspective, Redshift is designed to be run as a clustered system. And so you have a leader node, which is your SQL endpoint. You can connect to this, any of your BI tools, SQL clients, or existing applications using JDBC and ODBC and Postgres drivers. And the leader node receives your queries and coordinates execution of those queries across all of the compute nodes in your cluster. And the compute nodes are where your data is stored and where data processing takes place. That's where the query execution engine is operating on your data. It's columnar storage, and we try and do as much in parallel as we can. These nodes are loaded and backed up in parallel from Amazon S3. That's where the backups happen. And you can also parallel load from Amazon DynamoDB. And Anurag will be talking about some other enhancements we've made to loading as we go through. And then we also make available a single node variant where all of these are co-located. This costs it costs 85 cents an hour, and it's available and great for dev and test and for standing up environments quickly. And then as you scale up into production uses, you can grow from there. So just to talk a little bit about how we do things in parallel to really drive performance for you. So when you're running queries, you want them to run as fast as possible. And so when you execute a query, what the leader node does is it goes through any logical transformations or optimizations that it can do. And it then generates a physical execution plan, which is generated C++ code, which is compiled and then executed in parallel on all of the compute nodes. And then Redshift actually caches this compiled code and persists it so that it can reuse it if you run the same query again, even if your query parameters would change. And so all of this is designed really to achieve as much performance as we can on every single query. Data loading is also something that we do in parallel. And our goal with all of these parallel operations was really to have cluster size not be a factor. So if you wanted to load a terabyte per node into a 3-node cluster, it would take the same amount of time as if you were loading a terabyte per node into a 10-node cluster. And loading is done in parallel. Redshift has a modified SQL copy command. S3 was our initial loading point, and it's great because S3 is effectively the Chicago O'Hare for AWS. If you put your data on S3, it can really be consumed by any other service that speaks to it, which is virtually all of them. And so when you issue this copy command, Redshift will load every compute node in parallel simultaneously. And the goal here is to give you linear load throughput as you increase the number of nodes in your cluster. And Redshift takes care of automatically distributing the data as appropriate as defined by you across all of these nodes. You don't have to make any of those decisions regarding the physical layout except for defining how your data is, how your tables are created at create time. There's a concept called a distribution key where you can, when you define that, control how data is spread across the nodes. And we also support parallel loading from DynamoDB using the same copy command. And there you can specify the amount of read throughput from Dynamo that Redshift uses. And so we see customers that have DynamoDB in their stacks for low latency data capture, and then bring that data into Redshift using the copy command to run analytics on it in the cluster itself. Another operation that we manage for you is backup. And so backup to S3 is continuous, it's automatic, and it's incremental. So anytime you load data into a Redshift cluster, we'll automatically begin backing that data up into S3. And we only back up the data that's changed. And so that means that we try and be efficient with the usage of S3 storage for backup. And you actually get free backup up to the amount of data warehousing storage that you've provisioned. So if you have a 4 terabyte cluster, you'll get 4 terabytes free backup utilization on S3. Now these automatic backups, called system snapshots, you can choose how long they're retained. Anywhere from 1 to 35 days, that's configurable by you. And at that point, they automatically age out. You can also take your own user snapshots at any point, and those are kept until you explicitly delete them. And what this allows you to do is clone your cluster or your environment anytime that you need to. So for example, we have customers who will take a snapshot of their production clusters, stand them up in a dev environment to do some testing or development, and then once they have a model that they can reuse, they'll push that back into production. Or you could share snapshots with other accounts, perhaps a different group within your company, or if you're a service provider, share them with your client, allowing you to essentially migrate your configurations around as you need. So backing up is just one part of the story. You also need to be able to restore. And restore is a push-button operation. You simply select a snapshot and click the restore button in the console or use an API call. And once that's done, Redshift will stand up a new cluster and then start streaming data back onto it. And so as soon as the system metadata is available, you can begin running queries, and Redshift will stream in the data needed to respond to those queries from S3. And what this means for you is that as soon as your cluster's up and running, and typically as long as 1 to 5% of the data is back, most of your normal workloads will run normally. And so, for example, we may have 3 years of data in our data warehouse, but most of our queries focus on what happened yesterday or last week or last month. And streaming restore allows you to get to that really quickly. Resize is another operation that we have spent a lot of time working on and made a parallel operation. And so what this does is it allows you to scale your clusters as your data needs and analytic needs grow. And when you select Resize, you remain online for reads. We actually provision a new cluster in the background and do a parallel copy of data from node to node. And so if you think about it, say we had 4 terabytes of data per node on the source cluster. When you're moving to the target cluster, which is 4 nodes in this case, you'd only have 3 terabytes of data per node on the target. And so the time taken to resize is proportional to the time it takes to move that 4T from one node. Essentially, since it's done in parallel, it's really about the amount of data on each node on the source. You can resize up or down. We only charge you for the source cluster. And when the resize is complete, we automatically use DNS to move your SQL endpoint to point to your new resized cluster. And so you can scale without having to change your client applications or any code that you've written. And in addition, if you wanted to scale while remaining online for reads and writes, you could simply clone from a snapshot, resize your clone, and then cut over when you're ready. So a lot of flexibility in these options. Things like this are much harder to do on-premise, where you have to think about racks and wheeling them around. And from a resize perspective, Redshift lets you start with a single 2 terabyte node and scale all the way up to 100 of the 8 extra large nodes for 1.6 petabytes of compressed data in your data warehouse. And clusters have to be homogeneous. So if you're running the XL size, which is 2T, you can have up to 32 of those for 64 terabytes. And at any point, you can begin using 2 or more 8 extra larges. And the performance of 8 single extra larges is roughly equivalent to the performance of an 8 extra large. So it's really about thinking about your scaling increment and how your needs are expanding. From a pricing perspective, we've really designed Redshift to be very, very cost effective. And our goal is to allow you to analyze all of the data that you care about, not to throw away data just to fit it into a data warehouse that you've licensed and don't want to spend extra money for or have to deal with. And so we have really 3 pricing options with Redshift. What you're looking at is the price for the 2 terabyte node. It's under $1 an hour, 85 cents for our on-demand hourly pricing. And we have customers that during proof of concept will run clusters 9 to 5, Monday to Friday, delete them, save a snapshot, keep them deleted over the weekend, and then spin them back up again on Monday to resume testing. And so that hourly flexibility lets you really control your costs. And then what we find is that if you take the 2 terabyte node at an hourly rate and look at the cost per terabyte per year, that's about $3,700. We then offer a 1-year reservation where you commit to a 1-year term. And for that, you get a 40% discount. So effectively, your cost comes down to just over $2,000 per terabyte per year. And the 3-year term gets you over a 70% discount, bringing the cost per terabyte to under $1,000 per terabyte per year. And for top-of-the-market columnar technology, this is a radically new price point. And it's opened up Redshift to a ton of different applications, not just traditional data warehousing, but also big data and SaaS applications. We've spent a lot of time in Redshift thinking about security. And so with Redshift, you're able to use SSL to secure data over the wire. You can enable transparent data encryption, which is for data at rest, and that's AES-256 hardware accelerated. And every single block that's written to disk, whether it's a temporary spill or data that you load, is encrypted, and your backups are encrypted. And there's no direct access to the compute nodes, so they're walled off inside their own virtual private network, and so cannot be accessed. And all of our communication with things like S3 is also encrypted using SSL. And then you can choose to run this inside of a VPC, which is our virtual private cloud, which is a logically isolated portion of the AWS cloud, where you control networking, routing, and you can connect it via VPN to your existing networks. And Redshift has been through PCI compliance, as well as SOC 1 and SOC 2, so it's an area of focus for us and a priority for us. We also really take our duty of safeguarding your data very seriously. And so we automatically replicate data within a cluster. Anytime you load data, it's replicated onto different drives on other nodes in the cluster to help you deal with drive failures transparently while queries remain in flight. And we also continuously back up that data to S3, so you always have multiple copies of data in your cluster. And these backups, which are continuous and automatic and incremental, go to S3, and S3 is really designed for 11 nines of durability. And so what you have is all of the performance benefits of local storage and all of the benefits of durability that you get from the managed replication and automatic backups. We're also monitoring everything in your system continuously, so we can deal with component failures, node failures, we can replace nodes, and when those happen, due to streaming restore, your cluster's available as soon as that node's provisioned and connected, a matter of minutes. And these snapshots can be restored into any availability zone within an AWS region. And so if, for example, there was some issue, you could restore from snapshot into another availability zone as long as Redshift is offered there, and we're offered in at least 2, generally 3 availability zones in all the regions that we're in. Another thing that we realize is that data warehousing typically exists in the context of another set of tools around business intelligence, data integration, and software and services and expertise. And so we've been working hard to support the ecosystem around Redshift, and we're excited to see it growing. And really our goal with Redshift was to allow you to use the tools that you use today. So from an application and BI perspective, you can connect to Redshift using JDBC and ODBC and standard Postgres drivers that you can download from the Postgres website. So really anything that you have should work with the system. And the names that you see here are folks that have put Redshift through their internal testing and certified it as supported platforms but customers are using a wide range of products with Redshift. There's also the AWS Marketplace. Think of this as the app store for AWS, and here you can go to find software to use with Redshift. There are one-click deployments, a range of pricing options. One of our partners, Jaspersoft, has done a lot of work around an hourly model and the ability to auto-discover your Redshift clusters. So a range of options for getting up and running quickly, and that's something I definitely encourage you to check out. And from a feature perspective, we've been launching a ton. Our goal with how we do products at AWS is to listen to our customers and iterate quickly. We've expanded globally. We recently went into Singapore and Sydney, so we're in the States, Europe, and Asia Pacific. We've been working on our security certifications. We've added features to support full encryption from client-side encrypted files on S3 to encrypted clusters to unloading encrypted extracts if you need that, and have focused on really improving the manageability, query capability, and data loading flexibility of Redshift. And all of these have been driven by customer feedback, so I encourage you to let us know about what you need if you try the system, and if you're already using it, I'd love to hear about the features that you'd like to see from us. And with that, I'll turn it over to Anurag. Thank you.
I was having a flashback during that presentation because it's pretty much the same content I did this time last year. So let's talk about what's next. So normally in AWS, we don't really project too far forward. So this is mostly stuff that's going to be delivered in the next couple of weeks. That's about as far forward as we're willing to commit to you guys. It's a pretty high change environment. So a handful of the stuff was announced by Jeff Barr earlier today. Some of it will be new, but I'll talk to it in a little bit more detail. So Rahul talked quite a bit about our security story, which I think is, we've really tried to harden the service. We take our custodial responsibility for your data very seriously. One of the things we've added recently is hardware security module support, either in the cloud managed by us or on-premise managed by you. And what that does is that if you're running an HSM device on-premise, then you hold the keys to decrypt your cluster. And we only access those when we start up. And so if at any time you choose to, for whatever reason, turn off our ability to access the cluster, all of the data is unavailable, whether it's in backup, whether it's on the cluster, et cetera. So that basically helps people who are thinking about moving from on-premise but have a degree of uncertainty about the cloud, that they continue to own the ability to curtail access to their data whenever they choose. The other thing that's not on this slide that we've added recently is the ability for you to manage your rotation of encryption keys just through the console or through an API. And so that basically lets you, through an API model, run whatever policies you want to, rather than our trying to manage the policies for you. We've also added audit logging. So earlier today, Andy talked about CloudTrail, which gives you the ability to get all system activity up to S3. So we're a participant in CloudTrail, and so all of your Redshift API events will go there. In addition, we also are taking all the database activities, so the successful logins, login failures, queries, loads, everything like that, also pushing that to S3, and then it's available through the same variety of tools for you to analyze and understand what people are doing with your data. And finally, we've added SMS alerts so that you can basically configure an SMS topic, decide which things that you're interested in monitoring, whether it's security, maintenance, progress of things like a load, and do that also for a particular cluster as opposed to all clusters, and then based on which thing, whether it's an error, warning, informational message, and then have that communicated either via email or text. And so you might say that I want all warnings or errors for security for my production cluster sent to me on a text message, but for development clusters, I will maybe take a lower bar and only do that over email. So with these features, we hope that in addition to providing the manageability of the service on your behalf, we also start to give you visibility into what's going on, control over what's going on, so that you retain the same sorts of capabilities you have on-premise today. Batch operations. So Rahul talked about our ability to add copy from S3 that it runs in parallel, and that S3 is basically Chicago O'Hare. And I don't know about you, I prefer direct flights. And so one of the things that we've added here is that people have a multitude of different source data. So you might have something sitting in a Hadoop cluster or EMR as a managed Hadoop environment or Cassandra or what have you. And so what we're trying to provide here is the ability for you to run a copy command where you specify a shell script from which you're going to get information. Then you do a little bit of setup to be able to let us run SSH tunneling over to your EC2 node, or for that matter, your node on-premise that's a part of your VPC, and let us extract data. And so we think that this is an ability to not just make things easy through managing all the parallelization and so forth, but also make things possible, so that with a little bit of work, we can make these things available to you for a wide variety of sources without necessarily going up to S3. So cluster creation up till recently has been taking about 15 to 20 minutes. We're moving that down with warm pools to around 3 minutes. And so you might say, well, it used to take me 6 months to get a cluster. Why do I care about the difference between those two? And the fact is that you really want node replacements to be fast, because node replacements aren't just about initial cluster creation. They're also about handling failures. So if a node drops, and if you're running a large enough cluster, inevitably sooner or later a node will drop. 3 minutes of downtime is a very different story than 15 or 20 minutes. So what we're basically doing under the scenes there is that we pre-provision nodes out of EC2. We set up most of the environment for it, and then as you ask for that node, we have to basically do the VPC and final config to make it your node. Rahul talked about Resize and how we've made that a simple operation for you. We've also been working really hard on making it a faster operation for you. So in the past, if you're moving, say, I guess in this case, a couple of 8 terabytes of data off of an 8-node cluster to a 16-node cluster, it took about, more than a day, and we've reduced that by a factor of 4. That's still something that we hope to improve over time, but we're now getting into a range where it's really the network transfer rates that are dominating, which is exactly where you want it to be. So let's talk about performance and concurrency. So in our current workload management, what you can control is how many slots you want to make available. By default, Redshift comes with 5 slots that run queries. You can expand that up to 15 slots. You can expand the number of queues and distribute, how many, who goes to what queue and how many resources that goes to. So one of the things we've changed there is that in the past, the amount of resources available to each slot were the same. So if you had 15 slots, then they were basically all got 1/15 of the available memory on this resource. But if you think about it, you've got an environment where you might have a large number of concurrent point queries running and maybe some smaller number of batch queries, and you'd like to associate the number of resources accordingly. So in this case, if I had 5 queries, of which 4 were small, 1 was big, in the past, I was basically allocating far too many resources to that first number. And now I can set it up so that the second queue gets far more resources and presumably runs faster as the hash joins maybe run in memory and so on. So this is a feature that Approximate Count Distinct, where Count Distinct is something that we see a lot from our customers, particularly our ad tech environment, where people want to know how many people had an impression, how many distinct customers did I see with this campaign, et cetera. And count distinct ends up being an expensive operation because you basically need to sort and remove duplicates. So we've added an approximate version of that. So rather than saying select count distinct customers from campaign, you would say select approximate count distinct customers from campaign. So not much of a change, and we get on average about a 20x improvement, anywhere from 10 to 30. I mean, we've just started implementing this feature, so we're really interested in your feedback on it. And we're seeing about, certainly less than a 2% error bar. We're aiming for about a 1% error bar on that. So for, it's maybe not what you would use for financial data where you need to be right to the penny, but if you're running things like campaigns, impressions, and things like that, it makes a lot of sense. And the difference between an hour and a few seconds is significant. Distributed tables. So Rahul talked a little bit earlier about how we have the model to specify how data is distributed in the cluster. So you can basically, in the past, you were able to specify data is round robin. So basically, every new row goes onto a different node in the cluster, so you get a nice even distribution. And then we also provided data is hashed. And so the reason you might pick a hash version of data is that way the joins are co-located, and so I don't have to go across a network in order to satisfy everything. So what we've added now is also a third option, which is all. And so what we do in this case is that the data for a particular query, for a particular table would be replicated on each of the storage nodes. And if you resize, it's going to be copied to the extra nodes, either up or down, et cetera. And the reason you want to do that is that you might have, if you're running something like a star schema, a big fact table. You're certainly going to hash that out. And a bunch of dimension tables, which might be comparatively small. Let's say the months in the year or something like that. And so you really don't want to go across the network for that. You'd much rather have that come locally. And so there is a standard benchmark called the star schema benchmark, which is basically a star schema version of TPCH, which some of you may be familiar with. And so running that on Redshift before, we get a little over, somewhere between 2 and 3 times improvement, basically just by moving some of these dimension tables to be replicated across all nodes, which is a simple alter table command. Concurrency. So a lot of, basically all of the columnar data warehousing vendors are optimized to be able to run big queries fast. And so the notion there is that I want to basically throw a lot of hardware at an individual query. And so we've all been in some level of teens, or I shouldn't say all, almost all, I don't know all vendors, in the teens of concurrency as a result. So you can run much higher concurrency workloads on an OLTP system, of course, but you can't then use all of your resources for that. So we're now moving towards allowing you to increase that number to 50. And a lot of that has to do with workload resource management, as I expressed earlier. And so you'll have to be thoughtful about what, how and why you use this. So you'll have to experiment. But what the basic thought here is that if you have a mix of big queries and small queries, then you can run the small queries at much higher concurrency in one queue with a much higher workload, and then run the other ones with much more resource against them. Again, an area that we're going to continue to evolve over time. So that's basically the set of things that I'm prepared to talk about right now. So this is basically a eye chart which shows the various features that we've delivered over the course of this year since service launch. And you can kind of see from it both the notion of more things coming at a faster pace, and we're very much looking to that continue to be the case over time. And there's 6 weeks left in 2013, and we have significant plans for the rest of the year as well. With that, I just wanted to give you a sense of some of the other people that you can talk to about Redshift here in some of the other sessions. I mean, we're a vendor, vendors always carry suspicion. So, I think a little later today, there's a session from HasOffers, Aggregate Knowledge, and Desk.com, which basically are talking about how they're trying to get maximal performance from Amazon Redshift. HasOffers is talking about how to run loads very, very quickly in like a minute at a time. Aggregate Knowledge is talking about how to run very complex workloads, and Desk.com actually puts Redshift underneath their customer-facing website so they can run at high concurrency. Then tomorrow, Amazon, the data warehouse, is going to talk about how they've been using Amazon Redshift alongside their existing technology stack. And Amazon runs one of the larger data warehouses in the world, and so those guys have a ton of knowledge. And for those of you who are moving from enterprises or who have large amounts of data in situ, I think that'll be an interesting talk to understand how we think about things. And then the third talk here is, again, one where we have a NASDAQ talking about their experience, Outlook, which is a Nordstrom's company, and Round Arch Isobar. So.